All right, sorry, we're running a little bit late this morning. So let me pull up some things. All right, so the first thing I want to talk about today, I've had a little bit of time over this weekend to kind of mess around with LT-Spice and try to figure out what was happening with our input voltage signal. So I'm just going to quickly create a new schematic, and I'm going to make a very, very simple circuit. And so this is the circuit that I used to test things. Simply a voltage source in series with a resistor. Couldn't get more simple than that. If we go to the advanced settings on our voltage source, I'm going to make this guy for now 0 volt DC offset, 1 milliamp, or excuse me, 1 millivolt amplitude with a frequency of 1 kilohertz, which is the same that we used prior. And I'm going to run a simple simulation command for 5 milliseconds. And I can see that I get a nice and even sinusoidally varying voltage output. No surprise there. We've never had any issues when we have a 0 volt DC offset. When I switch to a 2 volt DC offset, however, I get garbage, hot garbage, right? And so this is very similar to what we saw for the input voltage when we had our sinusoidally varying source with a DC offset connected to our layout of our differential amplifier stage, which is both good news and bad news. Good news is that it seems like our differential amplifier stage is actually doing what it's supposed to do. Bad news is that LT-Spice is being real wonky. So what I did is I played around with things. And so if I jump this guy up to 5 millivolts and run a simulation, it's starting to look sinusoidal. If I keep iteratively increasing it, this is getting closer to what the input signal looked like on our schematic view. So partially sinusoidal with weird peak values. And as I keep on, let's try 20. Getting a little closer. Now it's starting to look a bit more sinusoidal. Closer to sinusoidal, and so forth. So let's see what happens if I do 50. Now it's a nice sinusoid looking thing. So this was interesting to me because apparently LT Spice has problems dealing with a small AC signal on top of a large, in comparison, DC signal. It's not until, you know, we're at 50 millivolts that this thing really starts to look sinusoidal again. And if we change our DC offset to 4 volts, per instance, it starts getting ugly again. So it has something to do with the amplitude of the AC signal in comparison to the amplitude of the DC signal that was causing us so many, I don't want to say errors, but so much confusion with regards to why our input signal was behaving very poorly. So with that in mind, I want to open up electric. Excuse me. And I'm going to open up our library. And go into the, let's see. Let's look at our differential amplifier schematic. Okay, so this guy currently has all 3 stages chained together. So on the left-hand side over here, we have our beta multiplier circuit, and then a bias voltage V bias P. Output of that is connected to the gate of our PMOS transistor, which is this guy right here, our current mirror. And then our current mirror is supplying the reference current to our differential amplifier. So if I go into the SPICE code here, I was playing with some things like this line that I'm about to delete was literally just trying to see what kind of voltage I would get if my voltage source was connected to nothing. It had no loading effects whatsoever, and it still gave me that weird thing, which is why I started playing around with values. So if we try a voltage, an input voltage that is got a DC offset, a sinusoidal input voltage with a DC offset of 2 volts. The sinusoid will have a 50 millivolt amplitude and a frequency at 1 kilohertz, which is exactly what we just had connected to our resistor in my previous little explanation there. And we simulate this guy. We see that we're getting a roughly sinusoidal output signal. I say roughly sinusoidal because we can see that there's like a touch of clipping on the positive peaks. And that may be because our output signal is approaching our, or not maybe, it's very likely that it's because our output signal is approaching our DC supply voltage. So I'm going to back this off just a smidge and try 40 millivolts. And still, the positive peaks the peak value for the positive half cycle, those still look not as I guess you'd call it tight as the ones on the lower half of the cycle, but it's a little bit better. So what I'm going to do now, I'm going to try to figure out what the DC offset of this is so that we can calculate our voltage gain. So for the positive peak, we have 4.827 volts. For our lower peak, 2.69666408 volts. So there is a difference of 2.131 volts. When I divide this by 2 and add it to my bottom, 2.69666408. I'm going to subtract 3.762. I'm trying to get this guy effectively centered around 0 or as close as possible. And then the next thing I'm going to do is plot V in differential input signal. And now let's track this gain. So I'm getting 1.06477773, and for the 40 millivolts, all right, divided by 0.04. So I'm getting a gain of 26.62, which again is right around what we were expecting. So I couldn't begin to tell you why LT Spice can't or does poorly at representing small AC signals on top of a DC offset. But yes.
LT Spice does a data compression, and the tolerance is, for mine at least, set to 0.0025, so it's too high for a AC signal like that small relative to the DC offset, but you can change that.
Okay, so where's that setting at then, Grant? Thank you.
So it's in Tools,
Tools,
and then Control Panel, and then Compression, and then it should be under Relative Tolerance.
okay.
Sorry, I just found that. I would have told you earlier.
Let's see what happens if we put it at
It says it makes the data file a lot larger.
Yeah, I'm sure it does. Let's see. Let's drop this down to 1. Let's drop it to 5, actually. All right. Yeah, so now we're getting a very nice looking sinusoidal output, which means our input is also nice and sinusoidal. So that absolutely seemed to fix it. So that was that one setting that was screwing everything up. Thank you very much for finding that, Grant.
No problem.
So what did you change it to?
Let's look tools. I changed, well, I thought I had changed it to 0.0001, but I guess it didn't save that, but now it's working. So now I'm confused again.
Very strange.
Because I literally just changed it. Pressed OK. I dropped my input signal down by a factor of 8, which 10 minutes ago gave us weirdness on our input signal, and now it's giving us normality. So since this looks like a more evenly balanced sinusoid now, for whatever reason, I'm going to take a moment to calculate our voltage gain again. So what I'm doing to subtract my DC offset is, again, taking our peak value, which is 4.0616779, subtracting from that our lowest value, 3.779296. So 282 millivolts. I'm dividing that by 2. And then adding that to our lower value, because if this is a perfect sinusoid, then if I take half the peak to peak, I'm effectively getting the amplitude, and I'm adding that amplitude to the value for the lowest point of the negative half cycle to give us our DC offset. .920 volts. All right, so it's looking like it's centered around that, and no goodness, what did I just do? Okay, change this. So 0 to 5. So I put volts and not millivolts. All right. Click on this. Grab my thing. All right. All right, 141.76249. Divided by our 5 millivolt input signal, 28.35. So still same ballpark. So everything's working hunky-dory there. All right. So our schematic representation of our op-amp circuit, let me circle back around to this guy, is behaving very, very well. My best guess is that if we tried this with a layout, it's still going to behave very oddly, and I'm still not sure why that is. So let's see. Delete this thing in its entirety. So let's look at this guy right now. So this is, without all that other stuff connected, this guy is the differential amplifier with the ideal current source biasing. Looking pretty good. I want to see tools. That's the damnedest thing. Every time I go through and change that relative tolerance, it sets it back, but it also starts working right. So couldn't begin to tell you.
Does it open a new window whenever you write the spice deck?
Yes, but I would think that it would save the prior files. Like when you write a spice deck, I have it set to completely delete the previous results and all that kind of stuff. But the configuration settings should stay the same between, because like, for instance, I have a white background instead of the black background for the plot functions, which is the default setting.
Mhm.
So yeah, I get what you're saying. I don't know what's going on. So let's just check out the voltage gain here. 4.057. Three point 7767591 divided by 2 plus 'So I'm calculating an out DC offset of 3.917 volts. Seems reasonable there. And $140.1474 divided by 5, 28.036. So yeah, voltage gains are very, very close to each other when this guy is biased with the ideal current source. So now let's incrementally change things by putting our current mirror in. And our current mirror has our beta multiplier, so let me go ahead and take that part out. All right, so this guy, VDS4 is the drain of transistor 4, which is the output of our current mirror. So I now have those guys tied together. When I go into my current mirror, I need to turn off some of these things. So I need to leave VDD on, otherwise the transistors won't turn on. I need to leave VGG2 on because that is our bias voltage. I need to turn off the thing that's forcing VDS4 to be 0 volts. I don't want to do a DC analysis of the circuit where I sweep that output voltage. And let's see what happens. Let me make sure I turned off that. Yeah. So it was still being biased by the ideal current source, which is why it was looking so nice. So I wanted to make sure we're doing this correctly. It's doing something. But I want to look at the voltage scale here. Right, so it is 4.57282 up to 4.57295. So we're looking at something's happening, but it's on the order of 120-ish to 150-ish microvolts. So we're still getting odd behavior. It is trying to do something. One thing I want to try here, and this is just, I'm putting a resistor in for the pure purpose of having something that I can easily determine the current through. So I'm just going to name this guy dummy because it's a dummy resistor, and it's going to have a resistance of, I don't know how many zeros I put there, but a very, very small resistance, so that any current that we see flowing through this resistor should be representative of the current that's being output by our current mirror. This is just me kind of troubleshooting what's going on. I'm going to have to connect metal 2. Okay, that did not do what I thought it would do, but it looks like I didn't need that in the first place. So it automatically put the contact there. Automatically put one there. All right. So I've got my effective short circuit represented by a very, very small value resistor put in. Let me just double check this. Yeah, okay. Tools, writes by stick. It's taking it a little bit to do the simulation. It's almost finished. I thought it was anyway. It says 100%, and now it's still doing other stuff. Still waiting. I would think putting one resistor into the circuit would not increase the level of complexity so much that it would take, I don't know, much longer than 2 seconds like it usually does to do the simulation, but apparently I was wrong.
It didn't like freeze up when you did it, like the program crash or something?
No, I can see at the very bottom that it's still doing things because it's doing fill-ins, whatever that means. So
Oh yeah, I see.
Dr. Hartman, did you ever get around to posting the lectures?
great question. I meant to address that when I got in, but I was running late and forgot about it. So I want to apologize because I did not do that. That is on my to-do list for tomorrow. I have some students that are graduating that I need to get their grades in today, as well as my 2 other classes today, which is preventing me from knocking it out today. So I'm very sorry that I did not do that, but they will all be up by close of business, as it were, tomorrow for sure.
Okay.
I'm going to, if this simulation ever runs, and we can look at things real quick. What my plan was for today was that we were just going to design a very simple output buffer, which would be literally nothing more than a source follower. So NMOS transistor with a source connected at the, with a resistor connected at the source, and use that as effectively just a unity gain buffer to pull our output voltage down from oscillating around 4 volts to oscillating around VDS SAT plus VTH, so somewhere in the region of 1 volt. And then was going to call it a day so I could get to work on some of that stuff. But this is taking a long time. I also realize I have not posted your take-home exam 2, as it were. I'm going to make that today and have that up this evening. And then the quarter officially ends on Thursday at 5 p.m. So that will be the official due date. However, the unofficial due date will be Saturday at midnight, and I won't penalize you for turning it in quote unquote late. So I'm not, what I'm doing is effectively trying to cover my butt and not make you do work after the quarter is over, but allow you to do it should you need that time.
Sounds good.
Oh my goodness.
I was going to say it's not something lame like it's not recognizing the resistor because of no spice code or something, right?
You don't have to put spice code in for the resistor.
Yeah, I didn't think so.
Yeah, if it did something like that, it would pop up an error message before before it started running the simulation. All right.
I've had LT Spice do this where it sits here and like cycles through these iterations over and over again, but I can't remember what it was that caused it. It was back in like circuits 2 or something. I just couldn't remember what caused it. I wish I could.
It tells me to press escape to quit. All right, so I did that. So it only did 700 nanoseconds. What I'm going to do, close that out. I think the resistor value may be too small. So let's make it like 1 milliohm instead. There we go. Yeah. So the resistor value, which is too small, I didn't care for it. All right. So ideally, my output signal wouldn't change, and it doesn't appear that it has. So that's.
You think that might be a tolerance issue?
I want to look at the current first before I make
Okay.
that. IR dummy. So that current is behaving rather wonkily, but if you'll notice, it has a value of literally nowhere near the expected 20 microamps. Like it's almost 1,000,000 times smaller than that, regardless of whether or not it's a DC signal, which it obviously isn't. So there's got to be some sort of weird loading effect that's happening, and I don't know why that is or how we can rectify it. So with regards to our, let me delete this. With regards to our layouts, as far as this class is concerned, the best that I can say is that if it works how it's supposed to work when we bias it with ideal, if each individual part works how it's supposed to work when we bias it with ideal sources, then I'm not going to worry about the fact that it doesn't work while we connect things because we're out of time. This is the last day of the class. So we've seen that our differential amplifier that we've designed, the differential pair stage, works exceedingly well when we're able to slap an ideal current source down there at the bottommost node. We know that our current mirror outputs 20 microamps, and we know that our beta multiplier reference is supplying the 3.88 volts that we need to bias our current mirror to output our 20 microamps. So we've seen all three of the individual portions work in our layout. And when we chain literally this design together in the schematic view, everything is working swimmingly. So I don't know, I wish I had more experience with this program to be able to figure out what's causing all these crazy issues. I might have to go across the street and talk to John Serio at some point, who's creates ICs for Radiance, and see if he can help me figure out why these things won't tie together right. But I kind of just ran out of time. Okay, so the last thing that I want to do then is we're going to make a very simple source follower, I think. The schematic first. So source follower, for those of you that don't remember, very, very simple amplifier circuit with a gain of approximately 1. So I'm going to call this guy transistor M1. It's an NMOS. I'm going to make it 10 by 2. I connect the drain to our voltage VDD. So let me export this pin as VDD. I made a little wire come off the gate, so I'm going to export that as VN. I need to move where it says transistor M1 out of the way. I need to set my splice model. I need to select the transistor and then set the splice model. This is an NMOS.
Dr. Hartman, does a grounding ring always have like 0 potential?
Only if we connect it to ground.
Okay.
Yeah, and the guard ring around our PMOSs will only have a potential of 5 volts if we connect it to VDD. Otherwise, it's just going to be effectively a floating potential of whatever it needs, whatever the source is at when we've tied them to the source.
Okay. I'm going to export this pin as Vout. I'm going to drop a resistor and let's call it a 5K and see what happens. Rotate it 90 degrees. All right, now let's write the spice code for this guy.
All right, so it's going to be multi-line text. This is the problem with Zoom. All right, so we need to turn our power supply on. I'm going to define my input signal as sinusoidal input. I'm going to give it a DC offset because if I just put the small a small sinusoidal voltage at our input with no DC offset, what would happen? Anybody got any idea?
It will be on for like half the time and then off for like the rest of it.
So if Vn is really small here, VGS, or so if Vn with respect to ground is really small, VGS, which is Vin minus V out, effectively what we should observe is that our transistor kind of really doesn't turn on. It should be operating in the sub-threshold region, which isn't going to give us the response that we're looking for, right? This guy works as a unity gain buffer or very close to unity gain when it's in the saturation region. And so we need to make sure that we're putting up enough of a DC offset on the input signal to force it to operate in saturation. Well, what the heck did I just do? I don't want text properties. I want to see what the text is. Okay. Got to start over. VDD, VDD 0, DC 5, VN, that's not a V. $1K. That does not say 5. All right, so I've exported my input voltage VDD and output. Oh, one last thing that I didn't do that I need to. So I need to export this guy and tell the circuit that it's ground. And actually, instead of having a 2-volt offset, I'm going to call it a 4-volt offset because that's more in line with what our output of our differential amplifier has been. It has a 4-volt DC offset, and then it's actually usually somewhere on the order of a gain of 28. But let's run this and see what happens. So I'm going to take Grant's suggestion, make this 0.0001, hit OK, close this, and then try rewriting it. Still wonky.
I think you have to hit run again and not close it and reopen it, like from the spice.
Right. Let's see. Oh, yeah, you're absolutely right. Okay, so we can see that we have pretty easily here. I'm going to call it a 1.705 offset voltage. So this guy's now, we've eliminated our DC offset, and we had a 5 millivolt input signal, and we're getting approximately a 3 millivolt output signal. So this isn't giving us positive gain. It's actually giving us a little bit of negative gain. I'm going to change that resistor value because that's a little less than I would like. A little bit of distortion.
The tolerance is going to be different for this one because of the offset.
The offset, we didn't change the offset voltage though. The only thing I changed was a resistor value. But let's see what happens. All right, so I made it even smaller. 2 point. All right. So our 5 millivolt input signal is generating roughly a 4.5 millivolt in amplitude output signal. So we don't have a gain of 1, but we're getting closer and closer the larger we make that resistor. This is, I'm going to call it good enough for me for now. So with that in mind, I'm going to attempt to slide this guy over, and we are going to drop in our differential amplifier schematic.
So is this effectively just like a voltage divider?
It's an output buffer. So what I'm trying to do here is if we hooked up, say, a resistor to as the load of our differential amplifier, because that resistor would be in parallel with the output resistance of our differential pair, if that resistor is smaller than a couple of mega ohms, which is what our output of our differential pair should be, we would see that it effectively shorts our signal to ground almost. This output buffer here is trying to make it to where we're carrying that signal over, but we're adding effectively an infinite, we're connecting the output of our differential pair to the infinite input impedance or thereabout of our source follower signal, our source follower amplifier, so that we'll get the same output voltage, but we could load it with something that wouldn't make it short the output to ground. If any of that made any sense. God, what did I just do? All right, so I'm going to go into the differential pair thing, and I'm going to turn off the transient analysis, and that's it, because we need our power to be on. And I have turned off the ideal current source. Our input signals are there, so everything else seems good. And then in this spice, I need to turn off VIN because we're letting the input of our source follower come from the output of our differential pair. I also noticed something here. I didn't tie my body to the source, so I'm just going to do that real quickly. That shouldn't have much of an effect. All right. So it's telling me that I need to turn off one of my VDDs. So let's turn off the one in the differential amplifier. This is where it's weird to me, because in the layout version, if I don't have VDD on in each specific portion of the circuit, it freaks out and turns transistors off. And in the schematic view, it actually treats them as all the same thing. So if I apply VDD once with my most latest spice code, it applies it to everywhere else it sees VDD. All right. Source follower. All right, here's crossing our fingers that this thing behaves well. All right, so we have a nice looking sinusoidal output. Let's measure our voltage gain. So our input signal was 5 millivolts in amplitude from our previous discussion. So what I'm going to do, so we have 2.84611725 minus 2.593536. So that's 252.63 millivolts peak to peak. I'm going to divide that by the peak to peak value of the input signal, which is 0.010 volts. So we have an overall gain of 25.26365. So it went from 26.8, I think, down to 25.3 effectively. But we have chained that guy there. So again, we are seeing that our schematic representation of our op amp that we've designed is working very, very well, and our layout, for whatever reason, on the individual stages is matching these characteristics, but when we tie them together, not so much. So I'll leave it to you guys to, let me go to electric, convert or create a layout file for this simple source follower, which should take less than 5 to 10 minutes. So that pretty much wraps up this class. I'm going to put a, I guess you'd call it like an end of class survey thing online. Feedback is just for me. Like some of you guys have already filled out the official evaluating your instructor thing, and I thank you for that. What I am interested in is what I can do in the future to make this class better. So any candid responses you want to give, I'm happy to hear it, because I'd like to do a better job of teaching this class. So if you have the time and are willing to give me some feedback, I would very much appreciate it. All right, so like I said, I'm going to post, I'm going to work on your exam today, post it online, hopefully this evening, and I say hopefully, I'm going to do it this evening. I'm going to tell my wife I got to stay up late and finish things up. She should be okay with that. I'm going to put a online submission portal up for your library file that we've been working on in this class, which so that I can look at your schematic and I can look at your layout view and just, effectively verify that you were doing the work that you were supposed to be doing. And as long as everything looks legit, you all should be good to go. There's been some questions about the midterm grade, in as much as I haven't yet graded it. I will get to that, but I'm trying to think of how to put this. I have been pleased with everyone's at least perceived level of participation in this class. I think particularly since the first test, we've had some good discussions and back and forth about troubleshooting and things like that. So I'm very pleased with everybody's performance. So I would be highly surprised if anybody doesn't wind up making an A in this class. Like, to do that, you would have to just not turn stuff in. So that's one of the benefits of effectively teaching a grad class, is I can play a little bit fast and loose with things. All right, anybody have any questions about anything?
You said the videos for the class will be uploaded tomorrow sometime?
Yes, I'm going to spend all day tomorrow editing and uploading those videos.
Okay, sounds good. I just
When will-
missed part of the beta multiplier stuff, so I need to go back through that and rebuild that circuit. So
Yeah, and the due date for that stuff is the same as the other stuff. Officially, Thursday at 5. Unofficially, if I can look at it before your grades are due on Monday, I'm happy. Like I said, I'm very pleased with everybody's level of participation and all that kind of stuff. So as long as you can show that you've attempted to do the work, we're on good terms.
sounds good.
Yeah. This quarter doesn't need to be any more stressful for anybody else. So let's make this class be, what it is.
It's much appreciated for sure.
Just a little tidbit, not that it's super helpful now, but just remember that you can divide the voltages in SPICE to find the gain.
Oh. So
You can just like add a trace and just divide the voltages that you want.
I'm not sure that I follow,
So we were like actually just mathematically finding the gain by division, right?
oh yeah. So you're saying, oh yeah, that never even,
Just crossed my mind just a second ago.
yeah, you can do the math. The only issue that I would have with that is that because the DC offsets for the input signal and the output signal are different, that may screw things up, which is why I went through and canceled out the DC offset every time.
Gotcha.
Because, yeah, like the output signal of our differential amplifier has a DC offset of somewhere around 4. So, we have 4 volts plus our small AC signal, and then our input signal was 2 volts plus a smaller AC signal.
Yeah, you're probably right. That probably wouldn't work.
Yeah, I was just trying to think if we could have done something with effectively maybe throwing capacitors in to block the DC portion of the signal, but again, at the end of the class, so I don't know.
Yeah.
That may be something to investigate for next time. All right, so unless anybody has anything else, I'm going to pop off. I hope you guys have a...
I got a question. I'm sorry.
Sure, Diego, what's up?
I got a question about the senior design presentation today. Is that okay?
Sure, absolutely.
So in the senior design presentation, you guys mentioned there should be an introduction section. So what do you want to listen in that section? Like it says spend the first...
In the introduction?
Yeah,
Okay.
yeah, like 1 to 2 minutes with introduction. So what kind of introduction is that?
Oh, that's literally telling the class your names and introducing the title of your project.
Oh, okay. Nice.
Yeah. Yeah, so always make sure when you're giving a presentation to let the people that you're speaking to know who you are. That is the purpose of the introduction section. It is commonly forgotten, but it's pretty important to let people know who you are.
Okay, great. And then one more thing in the project subsystems. So our team's going to plan to talk about the different circuits are going to be different kind of circuits that we're going to have in our project. Is that what it's supposed to be in project subsystems, or is there supposed to be something else?
So project subsystems, I would take that as, yeah, the different aspects of your project. So for instance, for you guys, you're in the fly ash group, right? Yeah.
Yeah.
So you might talk about if you went with the dielectric heater, you would need a couple of different control systems, right? You need a voltage control system, you need a frequency control system, you need a temperature control system or something like that. So those are the different subsystems of that approach. And then for the inductive heater, you'd need something similar like that. So it doesn't need to be in great detail. It's just granularizing, that's a hard word for me to pronounce, granularizing your project into smaller subsystems so that it's easily identifiable of effectively exactly what we did in this class. Instead of designing one big op amp, we took it piece by piece. Do that for your senior design project and explain how you're going to do it.
Okay, got it. Thank you so much.
Yep, no problem. And I should have you guys' report graded and returned to you before class this afternoon. I think I have like 2 sections left to read on it.
Great. Oh, goodness. Thank goodness. Thank you.
Yeah, and also I've talked with Dr. Batari about this, and we are, officially the deadline is Thursday, but we'll accept late papers because I'm a jackass and didn't get things back to you in a timely fashion. So
I'll take that one.
yeah, no, that's 100% on me of just getting bogged down in all kinds of stuff. So,
Thank you.
yeah.
Dr. Harlan, I have a question about a circuit I'm building. So I have an Arduino like running some servos, and it works fine, but if I load the servos too much, it shuts the Arduino off. And I think it's just pulling too much current to the servos. And so I was wondering,
you probably are pulling too much current, and it's overheating the voltage regulator on your Arduino, which will cause the whole thing to shut down. I've noticed students doing that a lot.
Gotcha.
In the 120 class by effectively, like if they run their little spark fun display at too high of a brightness, it'll do that exact thing. So it's overheating your voltage regulator because there's a reason that microcontroller is $20.
Gotcha. Do you think if I like throw a capacitor across the power rails that it would maybe help that, or just buy a bigger power supply?
So yeah, what I would do is I would run, because your servos should have like the signal. Your servos should be 3 terminals, right? One for positive power, the other is for ground or the negative power supply, and then the other is for the information signal that tells it, how fast to turn in one direction or the other.
Mm-hmm.
So I would run the servos power off of an external supply.
Okay. What if I can't do that? Do you have any suggestions for that?
I mean, you can't. The servos are going to draw. I would say load the servos less, because the servos are going to draw X amount of current, regardless of whether or not there's a capacitor in there, right? They need so much power to turn.
But so they only pull the Arduino off if I go from like full speed one way to like full speed the other way in like a really short amount of time. Like otherwise they work fine. So I only need it for those little short bursts, which is why I was thinking about the capacitor.
Okay, so you're thinking like effectively temporary energy storage there. Yeah, I'd give that a roll.
Okay. Sweet.
How quick of a time are you transitioning? Because that may require the use of a large capacitor, which is going to be, hard to do.
Yeah. So I'm building like a little self-balancing robot.
Mhm.
And I'm like writing the control system for it. So effectively, the better the control system is, probably the less time like it'll take to go from full speed forward to back. Um, but I haven't been able to really tune it well because it shuts off before I can do anything.
Right.
So kind of playing with that.
What kind of IMU are you using?
I don't know what that means.
Inertial measurement unit. So are you using a gyroscope or
Accelerometer.
3-axis accelerometer?
Yeah.
Okay.
And that seems to, like it's working right. And like I said, if I do it really slow, like in my hands, it'll like turn the servos the right way, and it works fine. And if I take the servos off, it works fine. But as soon as I plug the servos in and it goes from like forward to backwards, it just like it pulls the Arduino off for like a second, and then like it turns back on. But that's too long.
Right.
And then I'm tuning it with a potentiometer.
Mm-hmm.
So I
When
can't
you-
exactly.
You couldn't run your servos from external power. Like, how are you powering the Arduino?
Well, I have it on a power supply at the moment, but I've already like built the little chassis to like hold everything. And it's like all 3D printed, so there's no way I can like retrofit another like power supply on it.
Well, I mean, I was just thinking of literally you could clip a 9-volt battery to it.
Yeah, I guess I could try that. I think I have some room.
Yeah, I mean, try with a capacitor and all that kind of stuff, because if it's only happening when it's going from full speed in one direction to full speed in another direction, I mean, the key there is going to be then to mitigate how often that happens. But I
Yeah.
understand, if your Arduino dies, and that means your control system cuts out and your self-balancing robot falls, which is
Right.
what you
It's
want.
just a falling robot.
Yeah.
Yeah, I might try to take some capacitors from that power supply we built in electronics.
Okay.
They're pretty big. All right, thanks.
Yep. Any other questions?
Dr. Hartman, are you going to be in your office hours tomorrow?
Honest, over Zoom, sure. Am I physically going to be in my office? Probably not, because it's much easier to do my video editing from my more powerful computer, which is at home.
Okay. The time conflicts, I got signature for the 2 physics class. I got signatures from Dr. Sawyer on both of those.
Okay.
And is there a way I can do that through the online portal, you think?
If you can, so it's for time conflicts, right?
Yes.
Send me those, like is it a physical signature that you got from Dr. Sawyer?
Yes, it's physical. I can scan it.
Yeah, scan it and send it to me, and I'll send it into the registrar's office digitally and say, hey, I also agree to this, so let him register.
Okay. All right, I'll do that. Thank you.
Yep. Any other questions?
Hey, I got a question about a circuit that I'm designing for my team. Is that okay?
Okay, sure.
So, I was looking to the wah-wah pedal, and I was wondering, could you use the wah-wah pedal as a sort of frequency design, frequency control?
So yeah, I had actually suggested something like that to Kurt. And so like how a wah-wah pedal works, and the reason why, I mean, they can be expensive, but they're not nearly as expensive as if they had to use a tunable capacitor or a tunable inductor, is it's a potentiometer whose post is set on a gear, so that when you rock your foot up and down, it rolls that potentiometer forward and backwards. And that is moving the resonant frequency of the circuit up and down. So that is very similar to the frequency control you guys want. The only difference with the wah-wah pedal is that it isn't a resonator. So it's a resonant circuit in as much as it has one specific frequency, but you guys want something that rings out, right? Because you're trying to generate an oscillatory signal. Is that correct?
Yes. Well, we were planning to. We already have a circuit that's able to make the oscillatory signal. We're planning to connect that circuit to the wah-wah pedal. Would that be a good idea?
I'm not sure. Because the wah-wah pedal by definition is it's effectively a high pass filter. Or maybe it's
Is it not a band pass?
if it's a high pass filter or a band pass filter with a movable.
I think it's a band pass with a movable.
Okay.
Yeah, frequency.
So my concern with chaining your oscillatory circuit into that is that if you have, so you have a circuit at a fixed frequency going into a filter, if it's inside that filter's range, it's not going to move the frequency. Does that make sense?
Okay.
So
Yeah.
let me draw something real quick. I mean, if you want to borrow the wah-wah pedal I have in my office, as long as you don't like take it apart or anything like that, and see if you can use it in the way you're thinking of, I have no problem with that, but I don't think it's going to work. But I have been wrong on so many times, it's not even funny. So feel free to prove me wrong. There we go. Too much. All right, so what I am suggesting, or what I'm saying I think the issue is going to be, is that in the frequency domain, let me turn this to color. Yeah, there we go. So you have a voltage signal that is a function of frequency. And here is omega. So let's just say that you're able to generate a pure tone, which would be a simple sinusoidal function with no harmonics or anything like that for now, right?
Mhm.
In the frequency domain, that's an impulse, right? Hopefully you guys remember that, or you remember that from, I guess it'd be Fourier transform, maybe, or Laplace, I don't know. Your filter circuit, so this is my transfer function. Might look something like this. So if it's a band pass, omega low, omega high. So when you put this impulse function into this filter, if the omega of your impulse is between omega low and omega high, nothing's going to happen. If it's outside of there, you're attenuating your signal. So being able to move omega low and omega high around isn't going to change the frequency response of your input signal. It's just going to pass it or kill it.
So basically the wah-wah pedal function wouldn't be useful in this case.
Yeah, I don't think it would be. And again, if you guys have your oscillatory circuit and then want to put it into my wah pedal to see if you can use that to, and then measure the output signal on, say, a spectrum analyzer to see if it does anything, I got no problem with that whatsoever. But I don't think it's going to be applicable here. Like the reason why it works on a guitar is because of all the different multiple frequencies that when you pluck a string on a guitar that gets generated. But if you make an oscillatory circuit that's effectively only oscillating at one frequency, your filter isn't going to moving the resonant frequency. I guess what I'm getting at is you need to be able, oops, sorry. You need to be able to move this resonant frequency, not this one.
Okay. And for the oscillation circuit that we have, could it be possible that even though we have it set at a certain frequency, it could spike to another frequency, or it could decrease to another frequency?
Sorry, you were breaking up, so I couldn't understand.
So for our oscillatory circuit, could it be possible for, despite the circuit being set at a certain frequency, could it be possible for the output to move at a higher frequency for, I don't know, because of a spike maybe, or decrease to a smaller frequency?
I don't know. So what I'm thinking of right now, actually, so because your report specifically is fresh in my mind. You know, you guys are passing your AC signal through a full wave rectifier to generate a DC signal, and
Yes.
then you're using that DC signal to bias your oscillatory circuit.
Mhm.
You might want to look into how inverters and variable frequency drives work, because that takes you know, how a VFD effectively works is it takes your AC signal from your power supply, be it, you know, your transformer or a receptacle or something like that, converts it to a DC signal, and then uses an inverter, which is a device used in solar power generation to convert that DC signal into an AC signal. And a VFD specifically works by taking that signal from the inverter, which is now an AC signal at a specific frequency, and then moves that around. But typically speaking, so like a VFD would be able to change from on the order of say 30 hertz to 100 hertz or something like that. I don't know how large of a range that you guys are going to need.
We're currently planning to do like 10 kilohertz frequency.
So 10
Yes.
frequency, 10K. Okay, so that's pretty, with regards to, you know, how you would do this with motor controls, that's well beyond the range. Let me think about it,
All right.
because I know, I mean, I have power supplies with variable frequency. I know that you can do it. I'm just trying to think of how you would implement it in a cost-effective way, because the power supplies and stuff like that that I had to use, that I could change from on the order of, you know, a couple of kilohertz up to, I think, 25 gigahertz. That guy was like $40,000, and I don't think I want to invest that kind of money.
No.
So I'll need to think about how you can do something like that on a smaller scale that is not so costly.
Okay. Thank you so much for your time.
Could you use like a crystal oscillator?
And we're planning to use either Colpitts oscillator or a stable multivibrator.
Gotcha.
Op-amp stable multivibrator.
Yeah, so the multi-vibrator op-amp circuit is, I mean, that's something that interests me because it's a positive feedback circuit that has an applicable use. But I'm trying to remember what parameters you can vary in there to change the frequency. Because, so you're, yeah, I'll look into that too. Because that's where I had originally thought that you guys were going to go with your converting your DC signal into an AC. It's just a question of how do you tune that. All right, I got a better idea of what you're planning to do, which will help me try to figure something out. All righty, anybody else? All right, well, I'm gonna get to grading and all that kind of stuff so I can get these senior grades in and not have the registrar yell at me 40 times before 3:30. So thank you guys so much for your time, and I hope you've reasonably enjoyed the class as best as you can with all my my stuff. So I'll see you guys later.